All right, in this video, we're going to get a little bit mathy. We're going to go through some derivations of a few more maximum likelihood estimates. I'm going to do two examples, one of which is going to be the exponential distribution, which, as you recall, is a continuous distribution. We're going to find the MLE for lambda. And I'm also going to do the Poisson distribution, and there's a reason that I'm doing both. The exponential is more for practice. Poisson has one area that I want to kind of isolate, but the process is essentially the same in both cases. And I'll kind of list that over here very quickly. Our process in finding an MLE is we want to find the likelihood of our data. Second step is we're going to take the log. And I use ln. You can do base 10 log, but I'm going to do ln. We're going to differentiate with respect to our parameter. And then finally, we're going to set it equal to 0 to find the optimal point, the maximum likelihood estimate. So those are our steps that we're going to follow no matter what the distribution is, kind of a four-step process. Now, I'm kind of limited in my board space here, so I'm going to kind of use what I can as we move through it so we don't have to erase too much. We're going to kind of work through the problem, these steps, in order for both sets of these. So let's start with the idea of the exponential distribution. So I have, let's say, n random variables, n random samples from an exponential random variable with parameter lambda. And my goal is, I don't know what lambda is. All I have is my data, which is more realistic in any reason. I want to figure out what's the most likely value of lambda given my data. So the first step, I'll find the likelihood function. And if you recall, the likelihood function of lambda given my data, x1 up to xn, is simply the product of the probability density function. And for an exponential function, the probability density function is lambda e to the negative lambda. I think in our videos we might have used the parameter beta. Lambda is just another one I can use instead. All right, so I want to figure this out, and the nice thing is here, and this is something you'll get used to with practice, when I'm multiplying a bunch of things together, lambda times lambda times lambda n times is lambda to the n. And anything I have to the power, I'm missing an xi here, beta lambda, negative lambda xi, I would bring the product turns into a sum in the exponent. So e to the negative lambda sum xi. I would encourage you, if that step isn't intuitive to you at the first step, which it probably won't be at first, kind of get some practice with it. Convince yourself that this equation is correct, that all I'm doing is running that product. In fact, if you want, write it out and then see how this agrees. But now I have my likelihood. So I'm going to come up here and I'm going to find my log likelihood of lambda given x. And this x is just the vector of x's. So to take the log, again, some log tricks. N times log lambda, that's this part here. I can pull the n down in front of the log. And log is the inverse of e, so this would just simply be minus lambda times the sum of the x's. Once again, if it's been a while since you've done some of these conversions, go slowly. Make sure you can convince yourself that they're correct. The final step here is I want to differentiate, or third step, differentiate it. So dl d lambda. The derivative of the natural log function is 1 over lambda, so I'd end up with n over lambda. This is n times 1 over lambda minus the sum of the x's. This is my derivative, and finally I want to set it equal to 0. So n lambda hat minus xi equals 0. The reason I want to make it clear, why did I put a hat on? When I set it equal to 0 at this point, by setting this equation equal to 0, I'm actually saying this value is the optimal value. This is the value of lambda that optimizes it. Do some simple arithmetic here, and we end up, let's see, we'll end up with, I'll do it in two steps, n over lambda hat equals the sum of the xi's. Then I'll kind of do two quick steps, so this applies here. And I'll do two steps at once. I end up with lambda hat equals n over the sum of the x's. And if you want, you can also say this is 1 over x bar. We're able to show the parameter, the maximum likelihood estimate of the lambda is 1 over x bar. So if you give me a set of data, n points, say this is an exponential distribution. If you find the average of those values, take the inverse, that's the most likely value of lambda to have generated those points. If you want to add an optional fifth step here, and I'll kind of write in parentheses, you can check the second derivative. Because if you recall, if it's a maximum, this just proves it's an optimal point. To prove it's a maximum, I need a negative second derivative. If you want to do it quickly, I'll write it here, dl d lambda squared. I end up with negative n over lambda squared. And you can check that that is always going to be negative, which means it is indeed a maximum. This is the process you go through, and I skipped through it pretty quickly. But these are mathematical concepts that I'll expect that you can kind of review in your old textbooks going back. All right, so now let's go ahead and take a look at a second example. I'm going to look at a Poisson example, Poisson distribution, the maximum likelihood. Recall we did the exponential example. Now all we're doing, same 5 steps. We're going to start with our likelihood. So now my data, x1 up to xn, is Poisson with parameter lambda. My distribution, or I'll just write the distribution function first, is lambda to the x, e to the negative lambda over x factorial. And when we do the likelihood, I'll try to fit this in here. The likelihood of lambda given x is the product of this term here. So I'll write it out full bore first. Product of lambda to the xi, e to the negative lambda. There's no I up there because there's no x's. Xi factorial. And we'll see if we can fit this here. Same rules that we did last time. Lambda to the sum of the xi, because when the I is in the exponent, product turns into a sum. E to the negative n lambda, because now, remember, there's no I in there. It's the same as saying the sum of the lambdas. Sum of the lambdas n times is n lambda. Divided by, well, this thing in the bottom is pretty ugly. I really can't do anything with a factorial. The product can't really be simplified anymore. It's pretty nasty. And a lot of people get really turned off with this. They start to say, okay, this kind of looks familiar, this looks familiar, but this part, I don't really know what to do with that. So let's go ahead and we'll take the log. It's still going to be ugly, but we'll see what we can do. So the log would be, like we've done before, sum of the xi's log lambda minus n lambda, because that's the e to the log of e to the negative n lambda, minus, because it's now in the denominator, again, this log of the product of the factorials is really gross. If you have a log of a product, you can change it to the sum of the logs. That's okay too, but here's the big kicker. We don't really need to. We don't really need to, and here's why, and this is why I wanted to do this example. When I take the derivative with respect to lambda, the derivative over here would be the sum of the x's over lambda. Again, the sum of the x's times the derivative of log lambda, which is 1 over lambda. No problem. The derivative of this second piece would be negative n. And notice, what do you see over here? There's no lambda. And since there's no lambda, when I take the derivative, it goes away. I don't even care about it. This problem, while it looked very difficult because I have this gross part in here, when I'm trying to solve for the optimal value of lambda, this doesn't help. There's no lambda in it. This is it. And I'm going to set it equal to 0, so I get the sum of the xi over lambda minus n equals 0. Put a hat on that now. And when we solve it, I'm just going to write the answer here. We get lambda hat equals the sum of the x's over n, which is x bar. Pretty simple answer for all that work. We end up with, well, what's your best guess for lambda? It's x bar. We've proven, however, that based on this function, if you use the value of lambda as x bar as lambda, that's the highest value, the most likely value of your likelihood function. That's the most likely value of lambda. We'll give some examples in the homework that will allow you to try this. You'll find out a lot of times very simple answers come out, but it's one of those things that through practice we're going to start saying, what if we don't have nice, neat, closed forms? That's when we'll start to get to the computer and let that do it for us. But I want to give you a breakdown of what's actually going on under the hood.